All right, so this is for lesson 2.2, originally presented in class on September 8th. The do now was as follows. Which statement does not belong with the other three? Explain. So take a moment and try this problem. Pause the video, and then unpause when you're ready. All right, so all of these represent conditional statements, but only one of these three is not necessarily a true conditional statement. So if you look closely, you will notice that this fourth statement says, if you are an athlete, then you are a soccer player. While being a soccer player implies that you're an athlete, being an athlete does not necessarily mean you play soccer. You can be an athlete and play basketball or football. So this is the one that doesn't belong. The focus of this video lesson is inductive and deductive reasoning. A conjecture is an unproven statement that is based on observation. You can use inductive reasoning when you find a pattern in specific cases, and then you write a conjecture for the general case. So take a look here at example 1. Describe how to sketch the fourth figure in the pattern, then sketch the fourth figure. Take a moment to make any observations. Now, if you look closely, you will see that there is a relationship between the figure number and the number of equal pieces in the figure. In figure 1, there are 2 equal pieces. In figure 2, there are 4. In figure 3, there are 6. So we notice then that the number of equal pieces is twice the figure number. Each circle is divided into twice as many equal parts as the figure number. So figure 4 must have 2 times 4 equal parts, or 8 equal parts, and must look something like this. This is an example of inductive reasoning, where you make observations about something, you look for patterns, and then you use those patterns to make a guess or a conjecture. Now, your turn to try. Sketch the next figure in the pattern. Pause the video and give it a try. Unpause when you're ready to check the answer. Now, if you look at this, you will notice that all of the figures have stars. So we know that our fourth figure will also be a star. We also notice that with all of these figures, there's a portion of the star shaded. In the first one, we see 1, 2, 3, 4 points of the star shaded. In the second one, we see 1, 2, 3 points of the star shaded. In the third, we see 1, 2 points of the star shaded. Therefore, we could make the conjecture that in the last one, we will only see 1 point of the star shaded and the middle, just as all the others have. Once again, this is an example of inductive reasoning. Example 2. Numbers such as 3, 4, and 5 are consecutive numbers. Make and test a conjecture about the sum of any 3 consecutive integers. So what we're going to do is we're going to look at some examples, and we're going to find the sum of those 3 consecutive integers. We're going to see what happens. So let's start with the ones they give us. 3, 4, and 5. When we add 3, 4, and 5, we get 12. Let's try another example. So maybe 6, 7, and 8. When we add 6, 7, and 8, we get 21. Let's try another. How about 9, 10, and 11? 9 plus 10 plus 11, that gives us 30. Let's do a couple more. How about 12, 13, and 14? When we add those, we get 39. And then let's do a really simple one. 1, 2, and 3. And we get 6. Now, in order to make a conjecture about this, I want you to take a moment, pause the video, and note any observations. Unpause the video when you're ready to see if your observation matches mine. All right, if you look closely, you'll notice that there's some really interesting patterns here. But the one that stands out the most for me, so what I notice is that if I look at that second number in each of these consecutive trios, I notice something interesting about that second number's relationship to the final answer. Now, if I look closely, I can see that that second number times 3 gives the sum. 4 times 3 is 12. 7 times 3 is 21. 10 times 3 is 30. 13 times 3 is 39. 2 times 3 is 6. So I can make a conjecture here. And my conjecture is going to say the following. The sum of any 3 consecutive integers is equal to the second number times 3. And that's it. Inductive reasoning. Now it's your turn to try. Make and test a conjecture about the sign of the product of any 3 negative integers. Pause the video and give it a try. Unpause the video when you're ready to hear the solution. All right, so this problem says we want to make a conjecture about the sign of the product of any 3 negative numbers. So let's play with that. So how about we start simple? -1 times -2 times -4. -1 times -2 is 2. +2 times -4 is -8. Let's try another. -10 times -3 times -5. -10 times -3 is +30. +30 times -5 is -150. Let's try another. So -6 times -2 times -4. -6 times -2 is +12. +12 times -4 is -48. I think I see what's happening here. When I multiply 3 negative integers, the sign of the answer is also negative. So I can say that. The sign of the product of any 3 negative integers is negative. And that's it. All right, to show that a conjecture is true, you must show that it is true for all cases. Now that can be really difficult because the number of numbers we have available to us are infinite. So being able to show every case is generally impossible. But you can show that a conjecture is false by just finding a single counterexample. A counterexample is a specific case for which a conjecture is false. Let's take a look. Example 3. A student makes the following conjecture about the sum of 2 numbers. Find a counterexample to disprove the student's conjecture. The conjecture is as follows. The sum of 2 numbers is always more than the greater number. So let's try that. If I add 2 numbers, for example, 2 plus 4, the sum is 6. Which of the 2 numbers is greater, 2 or 4? 4. Is 6 greater than 4? Yes, it is. Now, that does make me feel like the student's conjecture is somewhat reasonable, but they're telling us here that we can find a counterexample. So we want to find an example where what they're saying does not hold true. So let's try as follows. What if instead of 2 plus 4, I add 2 and negative 4? So if I add 2 plus negative 4, I get negative 2. Now, which of these two numbers is greater, 2 or negative 4? 2 is. Is negative 2 greater than 2? No, it is not. Therefore, we have found our counter example. Another great counterexample for this particular problem could simply be 0 plus 1. 0 plus 1 is 1, and 1 is not greater than 1. Now it's your turn to try. Find a counterexample to show this conjecture is false. The conjecture. The value of x squared is always greater than the value of x. Pause the video to give it a try. Unpause the video when you're ready to hear the solution. All right, let's take a look. The best counterexamples for this one are probably 0, because 0 squared is 0, and 0 is not greater than 0, or 1. 1 squared is 1, and 1 is not greater than 1. Some other great examples that were provided in class today were fractions, so like 1/2. 1/2 squared is 1/4, and 1/4 is not greater than 1/2. All of these are great counterexamples. Okay, now deductive reasoning, the other type of reasoning, is a little bit more believable because it uses facts, definitions, accepted properties, and the laws of logic to form a logical argument. The laws of logic that we will be using today are the law of detachment, which says if the hypothesis of a true conditional statement is true, then the conclusion is also true. And the law of syllogism, which says if hypothesis P, then conclusion Q, if hypothesis Q, then conclusion R. Therefore, combining these statements together, if hypothesis P, then conclusion R. Let's take a look at how these work. Example 4. If two segments have the same length, then they are congruent. You know that BC is equal to XY. Now, using the law of detachment, what statement can you make? Well, according to the law of detachment, we know that if the hypothesis is true, so our hypothesis here is two segments have the same length. We have here two segments that have equal length. So our hypothesis is true, then the conclusion is also true. So because BC is equal to XY, we know then by the law of detachment that these segments are congruent. So we can say the following. Because BC is equal to XY satisfies the hypothesis of a true conditional statement, the conclusion is also true. So BC is congruent to XY. Now it's your turn to try. If the measure of angle R is between 90 degrees and 180 degrees, then angle R is obtuse. The measure of angle R is 155 degrees. Using the law of detachment, what statement can you make? Pause the video. Give it a try. Unpause the video when you're ready to check your answer. Okay, so for this particular example, we're going to use the law of detachment just like before. So because, we'll start with that as well. Now, we're being told that the measure of angle R is 155. So that's what we're going to start with. So because the measure of angle R is 155, we know that satisfies this hypothesis. So because this satisfies the hypothesis of a true conditional statement, the conclusion is also true. Now, what is the conclusion? Well, if it satisfies this, then it's obtuse. So, angle R is, in fact, obtuse. Law of detachment. All right, example 5. If possible, use the law of syllogism to write a new conditional statement that follows from the pair of true statements. Now, once again, the law of syllogism takes two independent conditional statements and combines them together because one statement's conclusion is the other statement's hypothesis. So if A, then B, if B, then C, therefore if A, then C. An example I provided in class was, if I have a cat, then my cat sheds fur. If my cat sheds fur, then I have fur on my furniture. Therefore, I can make the statement, if I have a cat, then I have hair or fur on my furniture. So we're going to be making a connection of these two statements into one. So if you look closely on A, you will notice that on A, we have two statements. If x squared is greater than 25, then x squared must be greater than 20. And if x is greater than 5, then x squared is greater than 25. You will notice that the conclusion of the second statement matches the hypothesis of the first. So we know then that if this occurs, then this occurs. So that x squared minus 25 is what connects the two statements. So we can say then, if x is greater than 5, then x squared must be greater than 20. Now on B, we have, if a polygon is regular, then all the angles in the interior of the polygon are congruent. If a polygon is regular, then all of its sides are congruent. Now, in this particular statement, we have a hypothesis, a conclusion, a hypothesis and a conclusion, but both of our hypotheses match, but there's no hypothesis that matches a conclusion. Therefore, we cannot use the law of syllogism here. Neither statement's conclusion is the other statement's hypothesis. All right, now it's your turn to try. Use the law of syllogism to write a new conditional statement that follows from the pair of true statements. If you get an A on your math test, then you can go to the movies. If you go to the movies, then you can watch your favorite actor. Pause the video, give it a try. Unpause the video when you're ready to hear the answer. All right, so we notice here that our conclusion here matches our hypothesis here. Therefore, we can directly connect this hypothesis and this conclusion. So we might make the statement then, if you get an A on your math test, then you can watch your favorite actor. Example 6. What conclusion can you make about the product of an even integer and any other integer? For this particular example, we would like to use inductive reasoning. Deductive reasoning. So we could no longer use examples. So we're going to use some definitions. We're going to make some common things that we accept about what it's saying. So first off, let's start with an even integer. We know that all even integers can be written as 2n, where n is an integer. So 2 times 1 is an even number, 2 times 2 is 4 is an even number, 2 times 3 is 6 is an even number, and so on. And we're going to let m be any integer. Now the question is, what happens if I find the product of this even number and this other integer? So we're going to take 2n and multiply it by m. We're going to find the product. 2n times m is 2nm. When I multiply an integer and an integer, n times n, it creates another integer. Let's call it p. So we're going to say that nm is p, where p is an integer, because the product of two integers is an integer. Okay, now we can see that this 2p matches the definition of even numbers. So we're going to say then that this product is even by our definition. Now, what can we state then? What conclusion can we make? We can conclude that the product of an even integer and any other integer must be even. All right, now it's your turn to try. Use inductive reasoning to make a conjecture about the sum of a number and itself. Then use deductive reasoning to show that that conjecture is true. Pause the video to give it a try. Unpause the video when you're ready to see the solution. All right, so for this one, we were looking at the sum of a number in itself. Let's start with inductive reasoning. So inductively, we can just look at examples. So let's start with 2 plus 2. That's 4. Let's do 3 plus 3. That's 6. How about 10 plus 10? That's 20. And then how about 12 plus 12? That's 24. Now, what I notice is that the sum of a number in itself is always twice the number, right? 2 times 2, 2 times 3, 2 times 10, and 2 times 12. So I can say the sum of a number and itself is 2 times the number. Now, to use deductive reasoning, we must use facts definitions. So let's let n be a number. And let's add it with itself. So n plus n is 2n. And we could see here that our conjecture is in fact true. All right. Example 7. Decide whether inductive or deductive reasoning is used to reach the conclusion. Explain your reasoning. So this is kind of the summation of the entire lesson. So let's look. Do we understand the difference of inductive and deductive? So part A says this. Each time Monica kicks a ball up in the air, it returns to the ground. So the next time she kicks the ball up in the air, she assumes it will return to the ground. Is that an example of inductive or deductive reasoning? Well, if we remember from before, we know that inductive reasoning uses examples and patterns, observations. And right now, Monica is observing that when she kicks the ball, it does return to the ground. So this is an example of inductive reasoning because a pattern is used to reach the conclusion. Now in part B, all reptiles are cold-blooded. Parrots are not cold-blooded. Sue's pet parrot is not a reptile. Now you'll notice that on all of these are all facts. These are statements of truth. Therefore, this is deductive reasoning because facts and laws of logic are used to reach the conclusion. All right, your last try of this problem. Decide whether the inductive reasoning or deductive reasoning is used to reach the conclusion. Explain your reasoning. Pause the video and give it a try. Unpause the video when you're ready to see the solution. All right, when you look at the specific practice problem, you'll notice that they give us facts. All multiples of 8 are divisible by 4. That's a fact. 64 is a multiple of 8. another fact, and then they use these two facts to come up with this conclusion. So this is definitely an example of deductive reasoning. Now that you've seen the lesson and taken the notes, go ahead and give it a try on the homework. Textbook pages 80 through 82, numbers 1, 2, 8 through 38 even, 40, 41, 43, and 47 through 50.